Hi guys, what a lovely day to do more physics problems. Today I'll bring a very interesting problem associated with magnetic field. What is the changing length of the spiral spring down? In the figure, we have n turns, radius r, length x0, and spring constant k when a current I0 is made to flow through it. So the first thing you need to know is why the length would change. Well, if there is a current I0, it will have a magnetic field. We know that, but we can't know for sure at every spot is a magnetic flux density, right? We just know that at the central here, it has the biggest magnetic flux density, B middle, and it goes down, 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 down. Here we have, at the open end, we have 1/2 B middle. This is the first thing you need to know, and I mean, you have to remember that. And now we are going to figure out the B middle. This is, you can memorize by a easy formula. B middle equals to mu 0. This is the space permeability times n times I0. This is the linear density of coils. So in this problem, n equals to capital N over x0. And now we are going to figure out the additional energy through it, because we would like to know how much energy is added up because of I0, and it will make the spring longer. We can know that because k delta x equals to F, and this F equals to dw over dx. Okay, so now we're going to find out the total energy, because the we can assume that x0 and n are big enough to let us neglect the open-end effect. So we just use this value as the overall value. Okay, and just remember, how can we calculate the energy density of an electric field? We use 1/2 times d. This is the displacement vector times E, and so in magnetic field we use 1/2 times H times B, and this is the magnetic field strength. This is the magnetic flux density, and recall that B equals to mu 0, mu relative times H. Okay, here we don't have another material inside the coil, so we will neglect this. The overall W would be 1/2 times B squared over mu 0 times the volume. This is pi r squared times x0. We'll just use x for instance. And we calculate the W over dx. This is just the coefficient here. We will use mu the b squared equals to mu 0 squared times n squared over x0 squared times I0 squared times pi r squared, and it gets the overall is 2 mu 0 x0 squared. Here we can yes, there is only one mu 0, n squared I0 squared times pi times r squared. So the delta x would be 2kx0 squared, and this thing above. There are a lot of mistakes you could make when solving this problem. The first one is you're going to figure out the magnetic flux density Bx. We can set here x equals 0, x equals 0, and use integration, but this is very hard, and it needs a lot of calculation, and you don't know if you can get it right. So next time when you're thinking and we're doing any problem associated with these conducting coils or spiral spring and has a spring constant, you're going to use this method, to calculate the energy and differentiate it with the length, so you can get the force. It's another Cambridge interview problem, and I hope you enjoy this video. If you have any questions, feel free to comment and I'll reply.